Good afternoon, good evening, and good morning. Greetings from Stanford University, and welcome to the 27th AEC Global Teamwork Final Project Presentation Cyber event. My name is Renate Fruchter, founding director of the PBL Lab, and your host for the day. The PBL Lab is the home of the AEC Global Teamwork course I've been teaching since 1993 with partners worldwide. Our vision is to transform our students' tool set, skill set, and most importantly, mindset, moving from working in discipline silos to work as a single, cohesive, interdisciplinary team and develop fully integrated solutions. Our aim is to prepare the next generation leaders and change agents for the future workplace and challenges that they will encounter. What is unique about this class is that it brings together students, faculty, and industry mentors from 5 disciplines: architecture, structural and mechanical engineering, construction management, and life cycle financial management. Students learn to collaborate in globally distributed teams to virtually design university buildings, addressing local hazards such as earthquakes, hurricanes, flooding, local labor conditions. I have to say, this year has been a great pleasure to mentor and work with highly motivated, creative, and committed students from Stanford and 12 university partners worldwide. Given the unprecedented COVID-19 challenges and shelter in place, we are organizing this annual event in cyberspace rather than having everyone back at Stanford for a final great, engaging celebration. For this purpose, each global student project team prepared a video story of their project evolution. These stories are reviewed and assessed by about 30 industry mentors prior to the May 8th cyber event. But before we dive into very exciting student presentations, I want to extend a big thank you to our industry and faculty mentors, alumni, and owners and sponsors who so generously dedicated their time, attention, and knowledge to our AEC Global students. In collaboration with industry partners, we defined 3 challenges to further foster the students' creativity, focused on sustainability, specifically this year, resilience, integrating project delivery, focused on the question whether to industrialize or not to industrialize, as well as shared risk and reward, and technology innovation, focused on intelligent interoperability between models and disciplines. Winners will be announced at the end of the cyber event, May 8th. So don't forget to visit the PBL Lab Project Gallery website to find out who this year's winners are. Last but not least, a special thanks for the generous support of our technology industry partners that enable us to continue to develop new ways of working and learning by leveraging the latest emerging technologies like VR, virtual reality, AI, artificial intelligence, parametric modeling and optimization, and embed them in the students' new daily work practices that they experience in this global teamwork class. And with that, let's move on to the student presentations.
Hello, welcome to Team Pacific's spring presentation. First of all, we would like to introduce ourselves, starting with the SEs, Mac and Dimitris, Architect Ada, MEP Lucas, LCFM Adrian, and Mary and me as CFs. We would like to also welcome our owners, Kostas, Ishan, Sebastian, Carolina, and Tobias, and also our super mentor Renate.
And discuss how our team connected over the last 4 months. Starting at Stanford, sitting together around the table, with enormous help from Renate, we formed our team. Less than a week later, we had started to collaborate and navigated the virtual world via Zoom, Discord, and VR. This is how you could see us sitting at home. But this is what we actually see when we navigate the virtual world. We previously saw working remotely in a globally distributed team as a challenge, but that became the new norm for us, especially with the unfortunate situation of COVID-19, which resulted in Mary to return to India and added one more time zone to our collaboration. Still, we managed to meet almost every day, and our Discord channel never sleeps.
We summarized our interdisciplinary collaboration and discovered that our team's major collaborators were at SEs, who were available to meet and discuss. COVID-19 made our schedules flexible, and at times it just took us 2 minutes to meet on Zoom. For team communication, we used Discord, Span and Miro for brainstorming and planning. We used OneDrive and BIM 360 to share updated files. We regularly did clash detections in BIM 360 Glue and used Iris VR for troubleshooting clash detections and visualization at least once a week. Due to the universities being shut, a few of us lost access to VR headsets. Despite this, we used the computer screen version and did well in utilizing VR in comparison to winter statistics. We use VR to conduct walkthroughs with our team and also with our owners. More often, we used it in subgroup meetings to troubleshoot and solve problems and to explain and check the feasibility of our ideas.
Moving on from the team process, first thing we did was the analysis of the site. Our building is located on a site belonging to San Francisco State University and will accommodate their engineering department. In the bigger context, the site is located at the edge of the campus, right next to the Lake Merced. Already while being together on site, we spotted a big opportunity to use the view to the lake as an advantage for forming our concept. In a smaller scale, our site is situated at the crossroad of the main street on the left, Lake Merced Boulevard. During our site visit in January, we discovered a missing pedestrian connection between Winston Drive and North State Drive.
There's a height difference between Winston Drive and North State Drive, making the access to the site only possible from the North State Drive. There's also an existing retaining wall on site that we can take advantage of. Also, the Bay Area is characterized by high construction labor costs.
The environment has a major impact on any building. As seen on the left, the wind at our site blows mostly from west and northwest side, with an average velocity of 10.5 miles per hour. The temperature stays relatively constant through the year. The third climate aspect is sun insolation, which affects the efficiency of PV panels. As we can see, the biggest insolation is from the southwest side. Our site is in the 7th insolation district of San Francisco, which has an insolation of about 500 kilowatt hours per square meter per year. As we can see in the graph, San Francisco gets the most rain between December to February and gets very little rain between June and August. The city has been the driest it has ever been in 150 years because of the high pressure ridge that diverts the rain as seen in the image. The humidity in San Francisco is very high with an annual average of 75%.
Here's the soil profile of our site. We kept the water table depth in mind during design to avoid dewatering, which will increase construction costs and time.
Regarding the hazards that need to be mitigated, San Francisco's location along the San Andreas Fault means that the city is prone to earthquakes. And of course that the structural system needs to be adapted to the seismic design requirements. As an educational building, which means that in case of failure, the risk to human life is high, it is classified as risk category 3.
The concept from beginning went through an analysis and a set of changes from winter to spring quarter.
The analysis that we did back in Stanford led us to first conclusions of how to connect the dots in order to answer the needs and opportunities of the given site. The first and inevitable connection appeared in the merge through the building between the opposite levels of the adjacent streets. It creates a possibility to increase the height of the floors to gain better interior perception.
During the grid, we presented the idea of a kinetic facade for producing electricity from wind. This worked as an innovative idea, but the calculations revealed that this was a rather expensive high-tech solution that wouldn't create lucrative gain for the building and owners. At the winter presentation, we presented two concepts, both of which represented our user-oriented design focused on using nature for sustainability gain. After the final choice, we've made an evaluation of the best aspects of each concept to decide which ideas are the ones to further develop in the spring quarter.
The development started with finalizing the input from every discipline to increase the sustainability as well as integration of disciplines in the design. The final outcome of our collaboration is presented in our integrated facade system that each of the disciplines contributed to.
Our final design presents an educational building with a user-oriented design that provides innovative facility for engineering department. The building corresponds to nature with green walls and blends in with the site due to the use of natural resources. The focal aspect that creates the form of the building is an integrated wooden facade that is crucial for harvesting water from fog and use it for operating in the building. The building is accommodated to the sun directions that creates a well-being atmosphere. The goal of the project is to implement a user-oriented design to connect occupants of the building with the neighborhood community while designing the facility engaging the collaboration between people. The goal is to be flexible and prepared to adjust to the needs of the user.
Nature can be interpreted either as a threat that needs mitigation or as an opportunity. Therefore, it is our goal to neutralize any threats posed by nature while taking advantage of what nature has to offer in a sustainable but also innovative manner.
Data is important for design, construction, and operation. It must be shared among all the disciplines in order to assure the integrity, accuracy, and consistency of it. The team has worked collaboratively in order to assure that the design is ready to be built, operated, and maintained.
The first goal that we addressed in the design was the connection to community, which puts the user on spot. Not only are we thinking locally of the users as university members, but also globally about the contribution to the surrounding neighborhood. To create a sustainable co-living community, the design supports and offers advantages to surrounding as well as daily occupants. Observing how the education is evolving from individual learning to PBL creates a possibility to adjust new built educational facilities to new methods of learning. The future faculty members are students and professors that put emphasis on collaboration and teamwork, that they take part in classes and lectures that are supported by virtual reality and digital cooperation. We combine the needs of the occupants from owners and faculty's perspective and created a building that connects learning and innovation through collaboration. The day of the future faculty member starts when he enters the site through the main plaza. It functions as a meeting spot and the main outdoor public space. Right after entering the building, we've designed a rentable area which can operate as a cafe.
A cafe with 700 square feet enables the public to use the building and to gain additional income.
During warmer days, the cafe has a possibility to open up to the plaza as an extension of rentable area. that connects it to the public space and outdoor meeting spot. The route for the building follows to the auditorium that accommodates the lectures, and it's the biggest area of the building. Additionally, it can be used as a rentable space. The clear visibility is achieved by the terraced audience.
Displacement ventilation located on 2 levels was designed to get high thermal comfort in the auditorium. The supply ducts and fan coils are located under the raised floor, while exhaust ducts are placed near the ceiling along the beams.
The design gives an opportunity to have an outdoor lecture space with the possibility to hang the projection screen. The location of the screen is the most shaded from all the facades, so the lectures can take place both during the day and evening.
Another space that functions as a lecture space are the large classrooms. The same space used are here as a rentable area for events and is designed to be prepared for the unexpected. Last month changed the perspective of resilience of the facilities into a whole different picture. As a response to a possible pandemic that might happen, our building plays the role of shelter for the neighborhood, for which the classrooms can be used to retractable seating. The advantages of the building for giving shelter are the availability of a kitchen and bathroom facilities, sensors in the building to measure and adjust the air quality, and the building management system which allows to separate the airflow from other spaces. With the fog catcher and the combination of PV panels and Tesla batteries, we can always provide water and energy, also during lockdowns. To keep the users of the building healthy, we are using an ultraviolet disinfection robot which disinfects the building also in normal waves of influenza. During possible lockdowns, we are insured against the loss of rent.
The idea of preparing the quarantine separated from the rest of the building is supported by the fact that both large classrooms could be operated only by the external staircase and at the same time be disconnected from the rest of the building. Afterwards, we enter the atrium, which is the central place of the building. Not only enhances it the social connections, but also could be used as informal collaboration space for individuals and teamwork. The focal point of the atrium is the staircase that is essential as a viewing spot to the Lake Merced nearby. To emphasize the atrium from outside and the view from inside, we designed the facade as free from any shading system. To prevent the users from glare effect and overheating, we improved the windows to low E double glazing with a low visual light transmittance. The sun simulation presents how the gray tinted windows stop part of the sun rays from passing through the glazing. The building is designed to provide not only educational spaces like classes, but also additional areas for collaboration. The western wing of the first floor is fully designated to students' collaboration. It offers multiple options of workspaces, from integrated in the facade individual spaces, through shared team tables, and assigned meeting and conference rooms. The communication area is included as activated stand-up brainstorming spot, which we checked in VR for our sessions. The emphasis on collaboration in the building is encouraged by the arrangement of spaces. The flexibility to rearrange the seminar rooms from 1 to even 4 makes it possible to adjust it to the current needs and increase the area for usable space. The building is designed to enable the connection between students and faculty members due to the mixing of faculty and student offices on first and second floor. The offices are treated with high attention due to their air and sun conditions. The sun is limited to overheat the rooms due to the setback of the facade and natural passive cooling system. Additionally, the building is using the underfloor air distribution to enhance flexibility of spaces and temperatures.
To design a building with high efficiency, we also need an efficient ventilation system. For the primary system, we have the reverse air heat pump, while for the secondary system, we have a displacement ventilation with fan coils, a four-pipe system, and a central air handling unit with heat and cooling recovery. The reverse air heat pump was chosen because of its ability to efficiently heat and cool the building by only changing the flow inside. It also does not emit any CO2 and has low operating costs because it is powered by our PV panels. The benefits of our secondary system are that it can provide an individual temperature at each space, which can be controlled by temperature and CO2 sensors, which can reduce heating and cooling loads because air with the desired temperature is distributed directly to the occupant zone.
We have to go to also connect financially to the community. Therefore, we tested the cash flow within a base and the worst case scenario by adjusting the costs and rents by 10% and the discount rate by 5%. The table at the bottom shows that we are even in the worst case profitable, so that we can reach the goal to donate 10% of our profit to student communities in all three scenarios.
The second objective of our design is the connection to nature, by creating a structure that is able to recover quickly from natural hazards, but also a building which benefits from what nature has to offer. So, addressing the earthquake challenge, we need to control our structure's response to it, and at the same time minimize repair and downtime costs. Therefore, the team aimed for a resilient but also sustainable structure. Glulam columns and beams form the structure's framing system, which is supplemented by CLT panels with 1.5 inch of gypsum topping as a fire protective layer. Moreover, CLT rocking walls are used as the lateral resisting system. So in order to understand how the rocking wall system is related to resilience, let's first explain its basic mechanisms. During an earthquake, the wall rotates but doesn't bend, and thus the damage on the wall is minimized. However, the damage is still there, but is confined to replaceable Kraft-Winkler fuses, which provide the ductility to the system and the resilient characteristic, making the building serviceable after an earthquake event. The self-centering capability is provided by the post-tension steel rods, which extend to the entire height of the building. Since the damage is concentrated in the fuses, the rods remain elastic during the rocking motion. The connection to the diaphragm and also the shear transfer is implemented with round pins, which are connected to the CLT panel at each level and extend until the surface of the wall. As the wall rocks, each pin moves in the vertical direction inside the slotted hole. And the dimensioning of the slotted hole depends on the maximum vertical displacement of the wall during an earthquake, and it's attained by the nonlinear dynamic analysis, which will be later introduced.
To further improve the rocking wall's resilience, the team will be implementing structural health monitoring by placing strain gauges on the Winkler fuses and load cells at the post-tension tendons anchors. These devices will be connected to a central system and a digital twin, which will be explained later. This allows for operations and maintenance to know when to replace which fuse and if a tendon needs to be retensioned.
We are transferring the biggest natural hazard of seismic activities with a landlord insurance, and we discovered that to get this type of insurance, it's mandatory to have the rocking walls. Our landlord insurance covers the costs for reconstructing the building after an earthquake up to $5 million, and it also covers the loss of rent during reconstruction.
Since we have a restricted site, the use of modal cranes is not possible. Hence, we have evaluated 2 cranes for our site, the tower crane and the crawler crane. The final decision leads to the use of the crawler crane because it is more flexible, easier to install, carries more capacity, and it's movable, especially for the installation of the rocking walls. Since they come full height, 42 feet tall, the tower crane must be at least 100 feet tall, whereas the crawler crane with the luffing jib doesn't need to extend its boom or jib length.
The substructure of our building is made of concrete to maintain consistency. Since concrete isn't as sustainable of a material as timber, the team decided to use carbon pure, which reduces the amount of cement in our concrete by injecting it with carbon dioxide. Also, with the use of the raised floors, a retaining wall around the perimeter of the building is required to ensure that none of the timber elements were in contact with the soil. Additionally, during a subgroup meeting between the SEs and CMs on constructability, the interior footings were combined as shown.
This is a site layout for the excavation and foundation phase. The excavation will be done with by excavators working together with dump trucks. After excavation is done, concrete mixer trucks and concrete pumps will join the operation in order to pour the foundations and retaining walls for the basement.
Here's the structural framing plan for level 0. The SEs and CMs collaborated with the architect early on to have regular grids and standardized structural members. The largest challenge on this level was the 47 feet span of the beams above the auditorium. And the team's solution was to use flitch beams and double beams. The steel plates increase the strength of the beam, while the wood prevents the steel plates from buckling. And also having the double beams reduces the load carried by each beam.
The construction phase consists of the use of the crane. The crane is an important equipment in the construction since all essential elements such as columns, beams, slabs, facade, and walls will be installed with it. Zones were established to help with order during construction, and these zones were used in the development of the schedule.
Here is the structural framing plan for levels 1 and 2. To avoid floating columns on the beams above the auditorium, the team decided to use the same double flitch girders as in the auditorium. Another change in the design from the winter quarter is the addition of the cantilevers around the building. A combination of glulam braces and continuous beams were used to face this challenge.
As said before, SEs and CMs have collaborated with each other in order to design for constructability. This is shown on the standardized structural members selected. In addition, we have optimized the layout for the CLT panels, in which we have only 4 different sizes. This has been possible due to the standard grade size from the very first concept.
Here are our typical connections. We're using a concealed knife plate for beam-to-beam and beam-to-column connections. Not only is the concealment beneficial for aesthetics, but it's also good for fire protection. For the column-to-column and column-to-concrete connections, we're using Roffelblas's pillar. And unlike in the detail shown here, chemical anchors will be used for the column-to-concrete connection. And then for continuous beams, we are using Simpson's strong ties CCCQ connection, as seen on the left. For the CLT panel-to-panel connection, we're using a spline connection. And then lastly, we're using seal hooked plates to anchor the CLT panels to the beams.
Due to the fact that water scarcity is a rising problem in California, we have introduced systems that support production of water from one of the most common phenomena in San Francisco, which is the fog. Our design is enhanced by the fog catchers integrated with the facade. Based on the study of a research group at MIT and the fog collector producer from Germany, we've decided to use a Lateral polyethylene mesh. The research group proposed an efficient system from stainless steel, but though it was more efficient in terms of water harvesting, the cost of production and much higher weight disqualify it from being a better option in the long run. The water is collected on 2 layers of the woven mesh covered by substances that firstly ensure that small droplets easily slide down into the collecting gutter integrated with the facade mullion, and secondly, prevent the mesh from being covered with microorganisms. The irrigation system is attached to the columns of the facade and brings the water through pipes to 2 water collectors located underground on site.
Due to maintenance, the fog catcher modules are clipped into the modules of the wooden facade and are mounted with profiles. The windows behind the fog catchers are openable to enable cleaning.
A majority of fog catchers are located on the west and north facade because the wind can increase their efficiency. One of the biggest advantages of the fog is that it occurs almost every day during mornings and afternoons, so our device can work for the whole year. The adoption of the fog catcher idea combined with rainwater and greywater collection allowed us to reduce water consumption by 80%, as the fog catchers were able to collect more water than both rainwater and greywater collection. The fog catcher can be used not only for harvesting the fog, but also as a shading system. we performed an analysis which showed that the system allowed us to reduce the insulation in our building by 27%, which greatly helped us reducing cooling loads. To provide the building efficiency and choose the most prominent placement of the shading system, we did a shading analysis which shows that the most sunny facade will be located on the south side. To reduce the sun's impact on the cooling load and also to prevent glare, we choose glass with low E and visual light transmission value on this part of facade.
During the subgroup meeting between the architect, SEs, and CMs, a connection detail for the facade modules was prepared in a way that is structurally sound, easy to construct, and does not negatively impact aesthetics. The blue elements were initially attached to the structure, while the red elements were initially attached to the facade module.
The installation of the facade will consist on having first the structure ready, then the installation of the facade modules, and then after that, the facade is installed on the floor below and the floor above. We can install the facade finish in between the floors. Finally, the fog catching net is attached and clicked into the facade.
Considering the structural system of the building, the following suppliers have been identified, and the raw material timber would be sourced from Canada, whereas the connections would be majorly from Italy. We then evaluated the possibilities of prefabrication with 3 elements. The facade module with the fog catcher was a major component, but the risks associated with this were very high. Due to the combination of fog catcher and the facade, there were waterproofing issues and rework necessities. The whole structure is made of industrialized glulam beams, columns, and CLT panels, as explained earlier. They have been made to standard sizes wherever possible, which led to the optimization of freight, thereby leading to lesser emissions. These industrialized panels are pre-assembled at site with the connections. The risk associated with fire rating is mitigated by using fire rating paints, and the risk of phytocontamination during transportation is mitigated by individual packing and by using a hydraulic boom or pressure wash. Installation of bathroom pods is cost neutral, but has a higher risk with regards to MEP flooding and earthquakes as the structure has a raised floor system.
Due to an IPD agreement, we implemented a risk and reward concept regarding the target construction costs from the TVD. The graph shows that we share a reward of $1.2 million with the owners in the financial best case scenario, respectively a risk of $1.2 million in the worst case scenario.
To track the prefabricated components, active RFID tags were installed at the fabrication yard after the quality testing of elements. Then the data is mapped. These are geotagged to enable logistics tracking, and after arrival at sites, these are inspected and quality checklists are tagged, and data is stored and used to track materials to enable just-in-time deliveries. It also enables an efficient billing system. Post-construction maintenance and inspection logs are linked to the RFID tags, thereby enabling easy identification and resolution of defects during the life cycle. These also provide data for a reliable digital twin for operation and maintenance. Rather than adopting the final line construction method, we decided to use assembly line method. The kit of parts for facade module have been explained earlier, while the shell consists of glulam beams, columns, and connections, which are all individually RFID tagged, allowing accurate defect detection in the long run.
To face the challenge of polluted air next to our site caused by traffic, we introduced an inside-outside integrated green wall system based on the rocking walls designed on the perimeter of facade. From outside, it cleans the polluted air and contributes to decreasing the amount of CO2 in the air. It is watered by moisture and humidity of air. From inside, the system is covered with living walls. From photosynthesis of moss in specific soil conditions that enhance the harvesting of electrons, it generates electricity for plug load. Based on average capacity of the battery and its need for power, we calculated that the amount of living walls in collaboration spaces let us charge either 500 smartphones or 300 laptops a day. Apart from generating electricity, the system creates pure air conditions as well as natural cooling.
To fully use the natural resources given on site, we also want to use solar energy. To do this, we designed a PV farm on the roof. To choose the proper location and orientation of the PV panels, we make the solar analysis in Revit. According to this analysis and diagram of insolation, we located PV panels on the roof and oriented it to the southwest direction. As we can see, the roof has enough space to 376 high-efficiency panels with power of about 170 kilowatts. For whole year, it can produce about 270,000 kilowatt hours. We used Insight 360 to determine the energy consumption of our building. We initially implemented a highly insulated roof and wall assemblies along with low E-glass for the windows, but as seen in the graph, that was not enough. To further reduce the energy consumption, we had to also implement a fog catcher facade, LED lights, daylight control sensors, and an efficient ventilation system. After considering all of these systems, we determined an energy consumption of 58 kilowatt hours per square meter per year. Comparing that to the amount of energy produced by the solar panels, we are using 32% less energy than we are producing. But what to do with the additional energy? Our proposition is to give one part of it to the university community as free energy for charging electric cars. It can encourage people to change their vehicles to more greener ones, which will be a climate-friendly process because of less CO2 emitted to the atmosphere. The rest of the extra energy will be given to the neighborhood in case of blackout. Since our building is only using energy that we produce, there are concerns about if they get damaged. To address this, we have Tesla batteries in our building that can store enough energy for about 2 days, which will be enough time to fix the PV panels. Finally, we can perform our STV analysis. Our team meet every target and we're able to reduce our water consumption by 80%, which is very good with the water problems in California. We're also able to have our building be carbon and energy negative. Here, we can see the history of our STV analysis. As mentioned before, water is our largest challenge, and we're able to improve every category by using nature, rainwater, solar energy, and moss in green walls.
We conducted an analysis how the fog catcher, PV panels, additional rent, and the use of a cloud service influence our cash flow calculation. Without the additional rent, we wouldn't be profitable. The yellow and brown line in the graph show that our project would have an earlier break-even point by relinquishing the equipment to harvest natural resources. One reason for this instance is that the batteries have a low refresh cycle and are still quite expensive. However, we also want to give the owners the possibility to assess the different concepts with intangible aspects in the value for money analysis. In this value for money analysis, the first 4 rows show intangible assets of the different concepts. To relinquish the PV panels, batteries, and fog catcher would mean to lower the service for the public, to have a low educational purpose, and to be less resilient. From a quantitative point of view, especially the relinquishment of PV panels and batteries shows a huge contradiction with having the lowest initial costs, but in the same time the highest STV in terms of need of electricity. In conclusion, the building with PV panels, batteries, fog catcher, and cloud service has the highest value for money, considering tangible and intangible assets.
Data is used across all the disciplines and will become an important aspect for the use of the digital twin.
Here's an example of how we determine the minimum live loads per AEC 716 on level 1. A superimposed dead load of 15 PSF was assumed to account for partition walls and MEP equipment. And then load resistance factor design will be used. And then the load combination 1.2 dead load plus 1.6 live load is expected to control the design. Here you can see the gravity load path for the frame, which is highlighted on the lower left corner of the slide. The structural analysis and design of the building, apart from the rocking walls, was done in Bluebell's RFM, a 3D finite element analysis program. The team verified that there were no serviceability issues based on the deflection limits from the IBC and used the load combinations dead load plus live load. The strength requirements were checked using LRFD and resulted in the typical girder width increasing from 5 1/8 inch to 6 3/4 inch. And then the side length of the columns supporting the auditorium beams were increased from 10 inches to 12 inches.
The results from the modal analysis showed that in the first two modes, the translational modes are the fundamental ones, whereas the third mode is torsional. A low-rise building like our structure experiences mostly the first two modes, therefore the location of the rocking walls strengthens the building's torsional resistance. Here you can see the lateral load path of the same frame. The load creates a tension load to the external right columns of the frame, then it's transferred to the rocking walls and columns and ends up to the foundation. For the simulation of the rocking wall system, the software SAP 2000 was used. Regarding the separate elements of this system, a few assumptions were made in order to approach its response as much as possible. The CLT panel was modeled as an equivalent braced frame using 5-inch HSS sections. The Kravinkler fuses were modeled as a shear spring with a backbone curve as shown in the figure. For the tendon, first we created a material with a bigger elastic region than the fuses and then simulated the tendon as a load. Regarding the uplift movement, a gap support element was used, which is very stiff in compression but has no stiffness in tension. The nonlinear time history analysis was implemented on the southern frame of the building. For that, 7 ground motions were selected and scaled according to the design response spectrum obtained by the site class and the risk category of the building. The procedure on selecting the appropriate ground motions for this structure was based on the fact that low-rise buildings are affected more by earthquakes with maximum acceleration at high eigenfrequencies. The analysis was performed in SAP 2000 and the average maximum interstory drift and vertical displacement of the rocking walls was obtained. And here we see the maximum story drift for each case and the average value, which is lower than the limit in the AEC standard. Moreover, the mean maximum vertical displacement of the rocking wall is presented as well. This value will be used to design the detailed connection of the wall to the diaphragm. And in this video, we selected to show the Loma Prieta earthquake and the response of the southern frame, including 2 rocking walls. Here, the rocking motion of the wall is visible. And as you can see, the maximum displacement is noticed on the top right node, and it's 3.75 inches.
We have used an SL framework in which we review the planned schedule that Alice creates with a logistics model in Fuser. This framework helps us identify the bottlenecks and reduce the potential risk of having delays during construction. Alice helped us identify the maximum crews that the project can have. If we decided to have more crews than that, the project duration won't be affected. This is called the infinite resources. However, because of labor and the space constraints, there is a practical maximum resources that the project can use. We have selected a schedule with the practical maximum resources in which the project duration is 246 days and the total construction cost is 12 million. With the results of Alice, we have modeled a 4D simulation, including logistics. In this simulation, we show how the building is built and what equipment is required at what time. It also shows if there will be any conflict between equipment. The simulation has shown us if it's feasible to install the crane and also the maximum length of the truck that can enter the site. The main equipment is the crane, which is used since erection of the level 0 until the installation of the facade. trucks come and go, delivering materials such as column, walls, beams, and slabs. With the results of ALICE and the 4D simulation, we have identified a logistical bottleneck. In this simulation, trucks are delivering the facade modules and interior work materials. For the crane to always be working, there will be facade modules on the material laydown area when the trucks carrying the facade are not on site. Besides this, after the installation of the facade module, there is a facade finish that must be done with the telehandler. However, because of the space constraints between the telehandler and the crane, this must be done at the end of the installation of the whole facade, where the crane is dismantled and carried out of the site. When the truck with interior work materials come, the telehandler must move to another position. As we have seen in the logistical bottleneck, the practical maximum resources would cause delays from a logistical point of view. As a result, the duration will not be as expected. We have decided to take into account those delays and use a less aggressive schedule. The result from this is a project duration of 300 days and a total construction of 12.2 million.
We used a model-based cost estimation to obtain and update quantities according to the model, and then used a unit cost database to link the quantities to the prices and finally create the cost estimation. With this data, we use the TVD spreadsheet to keep track of our targets and also make updates to the design according to the TVD. A cost tracking is illustrated here. Initially, the cost estimations were based on both the model and a few assumptions. By 23rd Feb, we achieved to estimate it based on the model, thus increasing data reliability. But a week before the winter presentation, as explained earlier, we scrapped out our winter bind facade idea and then replaced it with forecatcher facade. By winter presentation, we increased the area of facade, which resulted in a rise in total costs. We then started to evaluate different options for facade, whether to have it as a standalone option. Then a final decision to integrate the forecatcher with the facade was taken, and the rocking walls were converted to green walls, thus resulting in a surge again. Later, Tesla batteries were added to meet our project's goals of giving back to the community and connecting to the nature, resulting in a final estimate of $12.2 million. Major cost fluctuations were observed in shell, services, and specialty construction categories. Shell costs were increased when compared to the winter presentation due to the evolution of our design. There was a rise in services costs due to the addition of Tesla batteries and the setup. Specialty construction costs surged due to the conversion of rocking walls to green walls and due to the forecatcher facade. All these resulted in us exceeding our target by around $300,000, which still makes the project profitable in the long run, as it would reduce life cycle costs, especially water and electricity.
To sum up our work, we would like to show that our building scored 81 LEED points and earned the LEED Platinum certification. It means that our building is friendly for both its occupants and environment.
To connect the final calculations of TVD, STV, and LCC, we connected Excel to Palisade risk to identify which of the KPI has the highest effect on the cash flow. With that risk, we conducted 10,000 iterations in a Monte Carlo simulation, which results are displayed in the tornado diagram. Water and electricity costs have a low impact, what is the result of having a very low need of energy and water in the building. Next to the interest rate and the level of additional rent, clearly the TVD has the highest influence on the cash flow model. What makes it necessary to conduct its calculation very properly to not have a CapEx overrun. Other risks than the before mentioned CapEx overrun, for example, act of nature, liquidity, construction, or operation and maintenance risks, are addressed by different risk strategies. The main risk measures are avoiding by using software or fixed interest rates, transferring by using insurances or oblige construction companies to take the responsibility for specific risks, mitigating by the use of a digital twin of the building. The right bubble graph shows the effectiveness of our risk management. and only the risks we are responsible for.
We've prepared a summary of challenges addressed in this year's edition. We are answering the resilience challenge with multidisciplinary solutions that create a building ready for unexpected. We collect the natural resources given on site, we store them, and we share them with the users and surrounding community. Through the structure resilient to earthquake, thanks to rocking walls and its sustainable materials such as CLT, we create a shelter in case of an earthquake, and together with green walls integrated system, we reduce the CO2 footprint. To answer the demand of the water shortage, we collect water from fog and rain to reuse it in the building. The PV farm based on roof creates a possibility for us to be sufficient to the energy needs of the building, as well as to support the neighborhood in case of a blackout. In case of an unexpected pandemic, the building is designed to be a shelter to support the nearby community.
Our financial resilience is shown by calculating the covenant's loan life cover ratio as ratio of cash flow to outstanding loan, and the debt service cover ratio as ratio of cash flow to debt service. In the graph at the bottom, the minimal values for the requirements of the PPP contract are indicated by the two straight lines. The orange and green lines for loan life cover and debt service cover ratio show that we never breached the covenants during the whole lifetime of the building.
After considering the risks and rewards, we decided to install the fog catcher separately and to pre-assemble the facade assembly module, thus mitigating all major risks. Anchors would be provided at required locations and the fog catcher will then be installed. The pre-assembly of the structure will be carried out, and it was decided to not industrialize the bathroom pods and just to concentrate on the other two. This helped us to achieve our industrialization goals: reduction in on-site fatalities and incidents, waste reduction by transport optimization and standardization, 4-week schedule reduction and time certainty, along with optimization of LCFM costs.
To close the loop between AEC, MEP, and LCFM, we elaborated the concept of a digital twin, which combines the virtual model with the physical building to easily simulate changes in design, construction, or during the operation phase. But the concept is not only a tool for data storage or building information modeling, it rather increases the value of the physical building by adding live data, what for example can reveal user interaction and increase the user experience. The boxes at the bottom show the full potential of the digital twin. Rather than having all data stored and analyzed in silos, it can combine them to a life cycle data set. The videos show the benefits of the digital twin during the operation phase in case of an earthquake. So here, San Francisco is shaking. We are starting with the very unlikely happening of an earthquake. Me as the LCFM of the building, who is currently in Germany, gets a message on my smartphone about the earthquake. With Buro, who lives in San Francisco, I schedule a walkthrough in the building to check for damages. While I use my VR headset to be in the virtual model, Buro is wearing the HoloLens in the physical building. So we start a walkthrough while I'm sitting in my German office. We first check the atrium and some rooms, and then in one room, we detect a crack in the ceiling and roof. Here the full potential of the digital twin emerges. By comparing the physical building to the virtual model, the damage is noticed automatically, so the digital twin can send automated messages to the roofing company, facility manager, faculty, and insurance agent to inform them about the damage. Also, the PV panels are automatically cut off from the grid as we not have been on the roof yet. Just as we want to continue, a message from the health monitor of the building pops up in the HoloLens, which shows that the status of the Kravinkler fuses from the rocking walls. And there are obviously some problems while we are starting to check them as well. Arriving at the first fuse, we recognize that the red light already indicates a problem. By coming closer to the fuse, we detect that it is deformed due to the earthquake. And again, the digital twin recognizes the damage and orders automatically the construction company to fix the damage. So just remember, I'm still sitting in my German office and could solve these problems in rather a day than a few weeks. A week later, we again do a walkthrough with the same setting. Buro starts with his HoloLens. We first go and check the crack in the ceiling and roof, which is repaired. Afterwards, we check the fuse. Here, green light shows that everything is all right because also the fuse is not deformed any longer.
And to be honest, we cannot really believe that we've already come to the end of AEC Global Teamwork Edition. Surprising for us how quickly this couple of months passed by and how much we've learned during this time. Not only did we polish our skills in our disciplines, but we've broadened our horizons. We've learned, listened, and asked questions. Sometimes we've brainstormed without results, and at times had too many ideas at once. But eventually, we've created a global project which wouldn't be possible with any of us, without any of us. It couldn't exist without enormous help from mentors and owners. We would like to thank especially to Renate for truly being a super owner and super mentor. Thank you, our owners, for spending time with us late Sundays and co-creating the ideas for the building. Thank you, mentors, for being patient with us and answering our questions and teaching us. If you need to revisit our material, remember to check the video attached to this presentation. Thank you for spending time with us. Best wishes from Pacific.
Pacific.
Great presentation, ending with a bang. Very exciting, and thank you so much for sharing your great ideas with all of us. We wish you best of luck and look forward to the questions from the mentors.